All right, so the last part of this section is talking about Fleury's algorithm. So if Euler's theorem indicates the existence of a path or a circuit, one can be found using the following procedure. So if the graph has exactly two odd vertices, and therefore it has an Euler path, we choose one of the odd vertices as a starting point. And if the graph has no odd vertices, and therefore it's a circuit, we can choose any vertex as a starting point. So that's basically getting us to the starting point. That's where we start. Now, the number of edges as you trace through the graph according to the following rules. After you've traveled over an edge, erase it, okay? And if we're having it on here, if we draw a second line over it, that's kind of the same thing because we can't erase something that's not erasable. So we might just make an extra line on it. And this is because you must travel each edge exactly once, okay? And then that shows the erased edges later as a dashed line, so we can put in a dashed line. Now, when faced with the choice of edges to trace, choose an edge that's not a bridge. Okay, so if you make a bridge, guess what? You're not going to be able to go back the other direction. You're going to be a disconnected graph, and so that won't work. So travel over an edge that is a bridge only if there's no alternative. So that usually is the last time you go to be able to connect the lines. Okay, so what we're going to do now is we're going to come up with graph here, and we want to find the circuit. And we're going to use Fleury's algorithm. So what does that mean? It means we have to count and see which ones are odds and evens. So here we have two even, two even. 1, 2, 3, 4. That's even. 1, 2, 3, 4. That's even. That's even. And that's even. So guess what? We can start anywhere we want to. Well, let's start up in the top left corner just because we're just going to do that. I don't know why. And we're going to work our way around. And instead of erasing, like I said, we're just going to draw lines. So we're going to go down here. So that's going to be 1. And then the only place we can go here is here. Now, if we go over here, guess what? We're not going to be able to come in over here. So now we can go either C to D this way or C to D this way. It really doesn't matter. Let's follow the bottom path. Okay. Now from here, we go back here, we're losing this whole triangle part here. So we have to stay in this triangle part. Now we can go up or down, it doesn't matter, but let's go down, and maybe we should keep our arrows here. And now the only way to go after that is up here, and then down here, and then over here, and then up here. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. So that's the 8 pieces we're going to follow. And so our circuit is going to go from B to A to C, then we go to D, then to F, then to E, then to D again, back to C, and then our back to our beginning, which was B. Okay. And so that would give us an Euler circuit. Now, could we've done it another way? Yeah, we could have gone B to C, and then we could have gone to D, and maybe then to E, F, D, back up to C, then down to A, then up to B. There's a lot of different ones. Just because we found only one for this doesn't mean that there's only one. There's at least one, and that's one of them we found. And so that's what we're going to use for our circuit in this case. All right. So let's summarize Euler's theorem here. So the number of odd vertices, if there's none, basically they're all even, then there's going to be at least one Euler path, and there's going to be at least one Euler circuit. Now, if there are exactly two odd vertices, guess what? There's going to be at least one Euler path, but no circuits. And if we have more than two odd vertices, then we have no Euler paths and no Euler circuits. So knowing this will really get it so you understand how to determine if there's an Euler path or an Euler circuit. So knowing these, 3 items here with the corresponding paths and circuits will really help you for this section. That's all for this section, so let's stop here.